So this is a very short outline, what we call the membrane hypothesis of aging and cell differentiation. It has a quite complicated structure at first sight, but you should know that the basic problem we have to explain is that why the living systems are only relatively stable, we have a continuous replacement of our components, even in those cells which are not dividing anymore, for instance, the neurons, the myocardial cells, and so on. And the process is complicated, but step by step we could understand what are the essential ones. First of all, what are the causes of the damage and what are the reasons why this damage is damaging, first of all, the cell plasma membrane? Causes of damage are first the free radical induced cross-linking of proteins and lipids, which is the merit of Denham Harman, who suggested already late 50s that this can be involved in the aging process. And the other component which is important in the membrane damage is the polarization of the membrane. It's an electric polarization. About 100 millivolt negative polarity is built up on a distance of 100 angstrom. And this discharge, the discharge of this polarity causes an enormous heat production. And because this discharge is taking place only within 1 millisecond, about 1/5, 1/4 of this heat is not dissipated from the membrane. Physically not possible. Therefore, the membrane has a tremendously great speed of damage in its components. We know in the liver cell plasma membrane of rat protein fractions which have a half-life of 4, 5, 6 hours. It means that from 4 to 6 times a day it should be replaced. And this replacement cannot be done always with the same speed. And this should be explained why. And here we explain by this scheme that if the membrane is damaged, its potassium permeability decreases. If this permeability decreases, the intracellular potassium content grows, it increases. This is good for the excitability of the cell, because otherwise we would lose the membrane excitability. However, if the intracellular potassium content increases, it contributes to the shrinkage of the colloidal systems. Therefore, the intracellular colloids become more and more condensed and lose water. This causes a general slowing down of all enzymes. At higher physical density, any protein, any enzyme-driven mechanism slows down. It means we slow down the rates of RNA and protein synthesis. It means that RNA and protein turnover also slows down. The replacement of the damaged components also slows down. We have waste product accumulation in the cells, which is the H-pigment or lipofuscin. And therefore, the membrane is forced to work for a longer time with more damaged components. And this cycle is turning around so many times during the life of a cell as many times the protein turns over. It means that we have everything in the old system which is present in the young, just it is not able to work so quickly as in the young system. And the result is that you lose your capacity in physical sense, in mental sense, in any other sense. The learning ability decreases and so on. Now, if we just look some examples which prove the validity of this membrane hypothesis, is the measurement of the lateral diffusion constant of the proteins by the system, method which is called FRAB, fluorescence recovery after photobleaching. And in this system, we can measure the lateral diffusion very precisely. The two straight lines you see here belong to first the mus musculus, which is the common mouse, and the other is the Peromyscus leucopus, which is a wild mouse strain. And you see that they start at the same point, the lateral diffusion constant at newborn age, extrapolated. If we measure then in different real ages, we can realize that this is a linear decay of this lateral diffusion. And this lateral diffusion is so different between the two species as their maximum lifespan. This animal survives maximum 3 years, and this survives maximum 8 years. It means that the lateral diffusion components of the membrane are the very best parameters to measure the real age of the animals. As a matter of fact, if I established these regression curves and then we made blind experiments, it means that only the sex of the animal was known, not the age. Then the real age could be established by a plus-minus 2 weeks error. Now, because we are interested more in the brain cells than in the liver, we measured also in male and female brown Norway rats the lateral diffusion constant of the concanavalin A receptors, and you see that the very same linearity can be established. And this means that the physicochemical state of the membrane is really changing linearly with age, even in the brain cells.